In this lecture, we're going to study the concept of the derivative of a given function. First, some background. Among the many unsolved problems in mathematics during the Renaissance, there were two that led to the concept of the derivative of a function. Specifically, thinkers were concerned with the problem of describing the tangent line to a given curve at a given point. And they were also concerned with the seemingly unrelated problem of defining instantaneous velocity. The tangent problem, which in Western civilization dates back to the ancient Greeks and possibly earlier, asks how to determine the tangent line to a given curve at a given point. René Descartes invented analytic geometry in the early 1600s, and this revolutionized mathematics, since it gave geometric objects an algebraic interpretation and simultaneously gave algebraic expressions a geometric interpretation. This was a fundamental watershed in mathematics because it led directly to the solution of the tangent problem. As an example, consider this geometric definition of a parabola with vertex at the origin opening upward and symmetric with respect to the y-axis. A right circular cone is generated by rotating a slanted line about a vertical line. Take a right circular cone and cut it by a plane which is parallel to the slanted line. The resulting curve of intersection is a parabola. Here is the algebraic definition of such a parabola, thanks to Descartes. Any expression of the form y equals kx squared with k positive represents a parabola with vertex at the origin, opening upward, and symmetric with respect to the y-axis. If you are trying to create a tangent line to a parabola, it turns out the second interpretation is much easier to use. As an example, let's find the equation of the tangent line to the parabola y equals x squared at the point 2, 4. The idea is to start with an approximation to the tangent by picking a nearby point and drawing the line between 2, 4 and this nearby point. This line is called a chord line or a secant line. Notice that we gave the nearby point coordinates with symbols, P and Q, so we can move the nearby point when we wish. And notice also that to stay on the parabola, we required that P and Q be chosen so that Q is P squared. Now to get the equation of the tangent line, we're going to need its slope. Let's call it m. If we can find its slope, then we will know the equation for the tangent, since we know it must pass through the point 2, 4. So we approximate the slope of the tangent, approximate, mind you, by the slope of the chord line. M is approximately the difference in the y-coordinates divided by the difference in the x-coordinates of the 2 points PQ and 2, 4. That is, Q minus 4 over P minus 2. And that's equal to P squared minus 4 over P minus 2, since Q must be equal to P squared. Now comes the dramatic finish, thanks to having converted the geometric problem of finding a tangent line to an algebraic one. The slope of the tangent line is the limit as P tends to 2 of the slope of the chord line. In mathematical notation, m equals the limit as P goes to 2 of P squared minus 4 divided by P minus 2. This is a rational function which goes to 0 over 0. And we know how to factor the numerator and clean things up to get that m equals the limit as P tends to 2 of P plus 2, which is just 4. Then the equation of the tangent line, which must pass through the point 2, 4 with slope 4, is given by 4 equals the ratio of y minus 4 to x minus 2, which is equivalent to y equals 4x minus 4. Clearly we can do this at any point a squared on the parabola. The tangent line must pass through this point. Its slope is approximated by the slope of a chord line through this point and a nearby point P squared. So m, the slope of the tangent line, is approximately the ratio p squared minus a squared over p minus a, using these 2 points to compute the slope of the chord line. We take the limit as p tends to a to get the true slope. M is the limit as p goes to a of p squared minus a squared divided by p minus a. And again we factor, and the limit is 2a. Therefore, the slope of the tangent line to the parabola y equals x squared at the point a squared is 2a. And the equation of the tangent line to the parabola at this point is y minus a squared over x minus a is 2a, or equivalently y equals 2ax minus a squared. This calculation, and others like it, was actually carried out before the invention of the calculus, and surreptitiously introduced the concept of derivative. Definition: if f of x is a given function, then the derivative of f of x at x equal a is denoted f prime at a, and is defined by the limit as x tends to a of f of x minus f of a divided by x minus a when it exists. As the sketch shows, this is exactly the slope of the tangent line to the graph of y equals f of x at x equals a. Let's calculate some derivatives. If f of x equals k, then f prime at a is 0 for any point x equals a. F prime at a is the limit as x goes to a of f of x minus f of a over x minus a. And if f of x is the constant function k, then that's just the limit of k minus k divided by x minus a. The numerator is 0, the limit is 0. This is no surprise. The tangent line to a horizontal line is just the horizontal line itself. So the geometric picture would have given us a quicker answer. For a second example, if f of x equals mx plus b, then f prime at a is m for any point x equals a. Again, no surprise, the geometric picture shows why. We calculate f prime at a equals the limit as x tends to a of f of x minus f of a over x minus a, and that's the limit as x tends to a of mx plus b minus the quantity ma plus b, all divided by x minus a. You clean it up, you cancel the common factors x minus a from numerator and denominator, and you're left with a limit of m. As a third example, if f of x is px squared plus qx plus r, then f prime at a point a is 2pa plus q. This is not obvious geometrically, but analytic geometry makes it easy. F prime at a, as always, is the limit as x goes to a of f of x minus f of a over x minus a. And that's the limit as x goes to a of px squared plus qx plus r minus pa squared plus qa plus r, all divided by x minus a. Now you clean that up, and you collect the terms in p times x squared minus a squared, and q, which is multiplied by x minus a. And then you factor out the common factor of x minus a, which is floating all over the place, and you end up with just the limit as x goes to a of p times x plus a plus q. And that's just a polynomial, and you evaluate it at a as 2pa plus q. So you get the idea. You write down the expression known as the difference quotient, which in fact represents the slope of a chord line, and then take the limit. Some extra information. The notation for the derivative is not standardized completely. Any of the following are also used to denote the derivative: f prime at a, df dx at a, or capital df at a. Also, once we have calculated the derivative for an arbitrary point x equals a, the derivative is now a function in its own right, and we replace a by x in the formula for f prime. For instance, in the third example, we showed that for f of x equals px squared plus qx plus r, we have f prime at a is 2pa plus q. So we would in fact say, if f of x is px squared plus qx plus r, then f prime at x is 2px plus q. Now obviously we don't want to spend our lives computing derivatives from the definition, And our next goal will be to establish a set of theorems which will simplify the calculation of derivatives. However, for your survival on exams, it is important to be able to draw the picture, explain how the derivative is defined as the limit of the slopes of chord lines, and actually compute a derivative at a point from first principles. Here's an example of the type of question you should be able to answer correctly. For the function h of x equal x squared plus 2 divided by 2x plus 2, find the derivative at the point 2, 1, using only the definition of derivative. Also, define the difference quotient you have used and draw a picture to illustrate the geometric meaning of the difference quotient. Finally, find the equation of the tangent line to the graph of y equals h of x at this point, 2, 1. So you would write h prime of 2 is the limit as x goes to 2 of hx minus h of 2 divided by x minus 2. We always start the same way. And now put in the definition of h of x. You get the limit as x tends to 2 of the ratio x squared plus 2 to 2x plus 2. Subtract h of 2, which is 1, and divide the whole thing by x minus 2. And now clean it up. And you end up, when you cancel common factors, with the limit as x tends to 2 of x divided by 2x plus 2, which is just 1/3. So the equation of the tangent line to the graph at the point 2, 1 is y minus 1 over x minus 2 is 1/3. And you clean that up if you like and get y equals 1/3 x plus 1/3. And the relevant picture is straightforward. Now the question is, when can a function fail to have a derivative at a point? This is equivalent to saying, when does the limit which defines the derivative fail to exist? There are in fact several situations which can be described by pictures and the associated failed limit calculation. Non-existence of the derivative at a point will always happen when the function is discontinuous there. As a simple example, consider the function f of x defined by 3x for x less than or equal to 1, and 1 minus x if x is greater than 1. Let's show that f prime at 1 does not exist. The sketch shows that there really can't be a tangent line at the point. Let's see where the calculation fails. Since the definition of the function is different on each side of x equals 1, we do our limit as two separate one-sided limits. These are called the right and left derivatives at the point. First, we try the left derivative, which we denote by f prime at 1 minus. F prime at 1 minus is the limit as x goes to 1 from below of f of x minus f of 1 over x minus 1, just our old friend the difference quotient. And that's the limit as x goes to 1 from below of 3x minus 3 over x minus 1 equals 3. So the left derivative does exist at x equal 1. Now to the right derivative, f prime of 1 plus. That's the limit as x goes to 1 from the right of f of x minus f of 1 over x minus 1. The formula for f of x is now 1 minus x on the right. The value of f of 1 is still 3, and you're dividing this by x minus 1. So you end up with minus x minus 2 over x minus 1. The limit does not exist since the numerator goes to minus 3 and the denominator goes to 0. So the left derivative does exist and the right derivative does not. This means that the derivative does not exist since the left and right derivatives would have to exist and be equal. The derivative can fail to exist even when the function is continuous at the point. Geometrically, the curve has no jumps but fails to have a tangent at the point. The classic example is g of x equals absolute value of x. This function is defined by the formulas. G of x is minus x if x is less than or equal to 0, and g of x is x if x is greater than 0. So again we compute left and right derivatives. F prime at 0 minus is the limit as x goes to 0 from the left of the difference quotient. f of x minus f of 0 over x minus 0. And that's the limit as x goes to 0 from the left of minus x minus 0 over x minus 0, and that's minus 1. F prime at 0 plus, the right derivative, is the limit as x goes to 0 from the right of the difference quotient, f of x minus f of 0 over x minus 0. On the right, f of x is x, and so we get the ratio x minus 0 over x minus 0, and that limit is plus 1. So the left and right derivatives both exist, but they are not equal. Just to add to our little wagon of difficulties, here's one last example where the function has a vertical tangent line. The derivative is undefined because the slope of a vertical line is undefined. Let h of x be x to the 1/3. This function has the entire real axis as its domain. However, at the origin, the derivative does not exist because the tangent line is vertical. Let's calculate. H prime of 0 is the limit as x goes to 0 of h of x minus h of 0 divided by x minus 0. This first statement never changes. Just the point A changes. That's the limit as x goes to 0 of x to the 1/3 minus 0 over x minus 0, and that's just the limit as x goes to 0 of x to the minus 2/3. This limit does not exist as a real number, so the derivative does not exist. The limit can be described by the symbol plus infinity, since the difference quotient is x to the minus 2/3, is positive and unbounded as x goes to 0 from either side. As a final remark, I would like to point out that if the formula for a tangent line were the only motivation for developing the concept of derivative, generations of university students would have been spared the challenge of mastering the calculus. When was the last time someone other than a math teacher asked you for the equation of a tangent line? The major reason for the importance of the derivative is that it measures the rate of change of the function. In this context, it is best to think of the independent variable as time and label it t rather than x. For example, Galileo Galilei measured the distance traveled by a ball rolling down an inclined plane. You can describe this distance by the function s of t, a function of time. Galileo's experiments determined s of t reasonably accurately. What he really wanted to determine was the velocity of the ball as a function of time. It turns out that the velocity is the derivative s prime of t of the distance function, and it took the genius of Newton and Leibniz to independently discover this. And of course Newton went on to calculate the derivative of s prime of t, which he called the acceleration. The idea is that over a time interval from t equal a to t equal b, the distance traveled is s of b minus s of a. Then the average velocity over this time interval is distance traveled divided by the time interval. That's s of b minus s of a over b minus a, as the sketch shows. This is the difference quotient. It represents the constant velocity needed to travel the same distance in the same time. But keep in mind that these experiments involved gravity, so the actual velocity was really not constant. However, if we compute the average velocity over shorter and shorter time intervals, then we should get closer and closer to the instantaneous velocity. In mathematical terms, the instantaneous velocity v at time t equal a is defined by the limit v of a is the limit as b tends to a of s of b minus s of a over b minus a of the average velocity. But this is just the derivative of the distance function s prime at a. As an example, suppose that Galileo had determined that a particular ball rolled down an incline with distance s of t equals 4t squared. What was its velocity at any given time? This is now just a straightforward limit calculation. At time t equal a, S prime at A is the limit as B tends to A of S of B minus S of A over B minus A. And that's the limit as B tends to A of 4B squared minus 4A squared divided by B minus A. You clean that up and you end up with the limit as B tends to A of 4 times A plus B equals, and that limit is just 8A. This straightforward calculation of a derivative Galileo was unable to carry out because he lacked Descartes' marvelous invention, analytic geometry.